But before we really get into rotational, let's distinguish between what we're already familiar with. And that's translational motion. Translational motion is something that we already know. Take a box on a plane and you're pushing the box, right? How much ever it moved is well the distance. I mean, and that motion is called translation, is the point that I'm trying to make. Right? Why? Because that box or whatever object that you are moving is, with respect to the surroundings, staying the same. Like nothing is really changing. Right?
And we're going to talk about like simple translation, so just like one-dimensional motion.
This is okay. Yes. The thing that I'm going through right now is simple. Is one-dimensional, right? We're just pushing a box along a plane. But even if you generalize this particular example, I mean, I think I don't really need to know if we really have to go that deep into what the difference is between something rotating and like I think it's pretty intuitive. Like you can imagine something rotating, right? So that's basically the difference. And translational is what we're mainly used to and what we deal with when doing everything. So all of our equations of motion with acceleration, velocity, you know, the big five kinematic equations, the dynamic equations, all of them are translational equations because they're all based on the fact that the object itself is not rotating. Now, if it's rotating, we add things in the mixture, right, which is a little different.
So, yeah, when you have an object that moves along a line, you have like two things at first. You have the distance and the time it took to travel that distance. And if we're just assuming like a constant velocity, then in order to calculate that velocity, you can do, you know, distance divided by the time it took. Or if you want to know the instantaneous velocity, you take the derivative of the distance or the position with respect to time. And essentially, you start with position and you take the derivative and you get to velocity. And this is translational velocity. In terms of rotation, it's a little bit, it's not like trickier, but there are kind of two things that you can look at. Because the first thing that you can look at is the rate at which the object is rotating around your point. And so first off, you have the angular position, and what you can do is take the angle divided by the time it took to travel across that angle, and then you get the angular or the average angular velocity. And if you want to know the instantaneous angular velocity, you take the derivative of the angular position with respect to time. But there is also another thing. Oh, you can go ahead.
I just wanted to say one thing about the angular position thing, right? Like a lot of people, they're sometimes like, you don't really have a protractor just measuring the angle. Now, for those of you that remember our trig episode, which is, I believe, where we spoke about the radian, becomes incredibly important when talking about angular rotation, angular motion, sorry. So angular position, not really, again, measured with a protractor. It's mainly measured with, again, those that remember the definition of a radian or how to really measure it based on this and not a degree is very simple. So remember the whole point of rotating is that you can basically make your arc into a whole circle, right? I don't know if I explained that very well, but like wherever you are, if you are rotating, that means if you are experiencing rotating or like rotational motion, right? Then what that means your path is describing a smaller set of a circle. Like it can basically be traced out to a circle, right? The whole point to basically say, to measure the angle that you traverse, the angular position, you take the distance that you traveled, which is along the arc length, like we call it, and you divide it by the radius of this imaginary circle that you draw around this arc that you are traveling. Now, again, if you visualize that, you perfectly understood it. If you didn't, I don't know how good that was. But it's basically the angular position is simply a ratio of the distance that you travel on the circle to the radius of said circle, right? And it's equal to 1, that means 1 radian, when you exactly travel, hence the name, one radius equal of the circle, right? So when the arc length and the radius are equal, that means you travel the same radius, you basically travel 1 radian. And the reason it's so much easier is because now this is based off, so there's no, like, it can be generalized for every case. And the best part about the radian, if you noticed, is that it is unitless.